back here at Wits. I came here 10 years ago as a PhD student to visit, and now I'm here again 10 years later as a postdoc to give a talk to you all. So I'd like also to thank Karen and Brent also for the opportunity to giving me over this past 10 years in long-standing collaboration. So I'm a stable isotope geochemist, and I use usually these isotopes in high temperature systems. But when I was preparing to give a talk here, I asked the question, what do you want to talk about? And the answer was maybe not bushveld. So I'll talk about more about the deep subsurface of Earth. And when I say deep here, we're talking about maybe up to 3 kilometers in the upper crust. So I'm sure this is not very deep for many of the other folks in this room. This research was developed during my time at the University of Toronto, which was my first postdoctoral work in Canada. And this is something that really doesn't get a lot of attention that it deserves the geology courses. So I know I never had heard about this before when I was an undergrad or doing my master's. And what we don't really talk about is that the Precambrian crust holds this rich hydrogeosphere that is a hot topic these days. And the reason why this is a hot topic is because this kind of extreme environments might hold ideal conditions for holding life. So we can use maybe Earth as a laboratory to understand extraterrestrial life. So when it comes to our planet, the estimate is that out of the continental crust, about 70% in surface areas made up of Precambrian crystalline rocks. And this is counting both covered and uncovered areas, represented in green and in blue in this map. So if assume around porosity of about 1%, the upper part of this crust can actually hold up to 30% of the groundwater inventory, which would be between 8.5 million kilometers cubed, up to 13 million in some other estimates. And most of this water in the crust is actually saline. And so this water, this hydrogeosphere, has the potential to sustain life in isolation over long geological time periods. And also, of course, these waters that we see that have been found in many mines are hypersaline normally, and they are associated with gas occurrences. But little is known about the origin, evolution, and residence times of these fluids up until about a few years ago. And okay, a few years, maybe 20-ish. But over the past 6 years, there was a big boom in publications about this subject. So why do we care about this? So as I said, we can use this as a proxy to understand extreme life and extreme life conditions. We can understand how water and rock interact over geological time. And especially, one thing that is very underappreciated, especially in papers, is mine safety. Because many of these times, like these fluids are found when you're drilling in the subsurface, and it can cause accidents, and there have been deaths because of this. So, distribution of fluids in the Precambrian crust. So there we are in the surface, where you have your sediments, you might have your open pit mine, and the subsurface in there has fractures. And these fractures can be hydrogeologically open if they're closer to the surface, but as you go down in the crust, you can get increasingly isolated with that. So some fracture networks can become sufficiently isolated, and if they get sufficiently isolated, they will preserve fluids over geological timescales. Showing this, for example, in the context of a mine. At the top of the figure, we think this is the surface, and as we go to the bottom of the figure, this feeling gets increasingly increasing the depth. So at the top, for example, borehole 1, it's crossing a series of fractures that might be slightly more connected. And so when you have this borehole, you have water coming out of it. It's gonna be maybe a little bit more like characteristics of meteorite water or something connected to the surface. as you go down, you see the fractures tend to be more sparse, and they tend to be disconnected from each other and from the surface. So borehole 2, for example, if you're cutting, if you're drilling through your rock, might intersect fluids that have been isolated for a long period of time. And when I say fluids, you see here in the left, you have water. And when this gets depressurized, the pressure goes off as the drill, it dissolves also gases that have been in this. So this is more or less what it looks like inside a mine. So for example, you might have your borehole. The left one, this is borehole on the ground, so essentially looking from up and to down. So you have water and you have the bubbling of gases coming up. But for example, the two pictures on the right, saline groundwater. How do you know it's saline? We'll go into this later. So I will divide these questions into 3 of them, and I will start with the first question about fluid residence times. How do we know like they've been there for a very long time? So again, we know the fluids are there. There is a preservation potential. We use noble gas geochemistry to be able to evaluate residence times of fluids. So this is calculated by essentially measuring different noble gas isotopes, and particularly of interest are radiogenic helium and argon-40, nucleogenic neon-21, and physogenic xenon-136. And they accumulate over time because you have radium, thorium, potassium radiation being emitted interacting with your rock, which will then, and then in these fractures you can accumulate these gases. So we use this to determine mean residence times of fluids and temporal evolution of fluids, and there's also spatial variations in fluid residence times. So this work has been done, and this is a compilation of data that has been obtained so far. So this is probably the most recent encompassing data set that we have. So for reference, the ocean has a mean residence time of about 4,000 years. So this is a log scale in years at the bottom. For example, argon, I just put for comparison at the top. The hatched bar, about 800 years. So oceans and surface processes in general have very small residence times. When we move on to Finland, we only have data for Outokumpu, the drill hole. This gives us an age between 17 and 58 million years, which is a long time, but we'll see that it might not be that big actually, long. In Canada, you also have ages between like 50, then you can range up to 500 million. And Kiprik, which is the most studied site so far, yields ages up to almost 2 billion years. So it means this fluid and these gases that were intersected by the boreholes and subsequently collected by the scientists have not seen like light of day whatsoever for 2 billion years. Here in South Africa, a lot of research has been done in the past 20-ish years. I think I'm going to highlight especially Kotsong, which is the mine that is about 2.5 hours away from here, uranium and gold, that also is giving over 1 billion years old mean residence time for argon ages. But in other mines, we also have some potential for long residence times. Beatrix mine, Wolf, and Driefontein, all of these have been studied. There are issues. The noble gases are a little bit finicky, which means that it's hard to measure, but also sometimes hard to interpret. So you see 2 data sets, one that is a closed color bar, and the other one that's hatched. So they use different modeling to be able to estimate the ages. So the closed one assumed that all noble gases have been produced then stayed in situ. The open hatched bars external flux model will potentially assume that some of these noble gases have been produced elsewhere and then put in the system. But we're still talking about some mines with residence times, ages in the 100 million years timeline timescale. So second hypersaline fluids. So for long, people have been finding this. It's not something new, like that is just happened, but there was no good explanation. So for example, some people would interpret this as maybe seawater that was evaporated and got trapped in these rocks, depending on the system. But we know that that's not exactly the case. And through geochemistry, we can evaluate this and explore alternative explanations. So two of the best characterized systems with longer residence times, Kidd Creek and Moab mines. So for you to have a sense of what kind of depth we're talking about here, when you're talking about these fractures that have been sealed off, at least 2.4 kilometers at Kidd Creek. We have 2.4 and 2.9 depth sampling, but also Moab around 3 kilometers deep. And our ocean, our current ocean, has a total dissolved solids around 35 grams per liter. And if you look at this graph, we have total dissolved solids at Kidd Creek around up to 230 grams per liter, and in Moab around up to like 246 grams per liter. So this is very saline. This is many, many times more saline than our ocean. This water like really smells badly, if I may say so. And it's an experience to smell it. Yes, and you can see that overall these waters get classified as calcium, sodium, chlorine water. Another comparison here, and in log scale, so the differences might not be, they might not look different. So as in red, we have our average river composition. The TDS is below 1 gram per liter in general. So in log scale, you can see how much more ions these waters in the deep subsurface actually have in their composition. So it's fair to call them brines at this point. And why does this happen is an answer that we can try to answer with isotopes. So in this case, we use oxygen and hydrogen, of course, to look at the composition of water. And I'm not entirely sure how much people know about this type of isotopes and the hydrogeology. So I just wanted to explain a little bit that the global meteoric water line is defined as the delta hydrogen equals the delta oxygen plus 10 per mil. And this is essentially a constant, a linear relationship. And essentially, like precipitation and snow worldwide should fall on this line. There's not many processes that will actually deviate them from this. The processes that deviate them from this are expressed in this figure. So for example, if your oxygen isotope changes, but your hydrogen doesn't, and this is horizontal relationship, you might have a low temperature exchange with rock minerals, high temperature exchange with rock minerals go the other way. So when you obtain a data set, you are able to evaluate essentially what's going on, like why like the isotopes might or might not have had like any kind of change. So when you look at Moab here in South Africa, you see that the Transvaal Dolomite Aquifer falls within the global meteoric water line. And this was collected at a 1.2 kilometer depth. So this is also like deep water, but still with a meteoric connection clearly, because it does fall in this global meteoric water line. You see the surface water of the mine in yellow up in the right upper corner. But when you analyze the Moab brines collected at 3 kilometers down, of course it's very shifted to the left. And you actually don't see much connection between the brine composition and what you would be seeing, like for example for the surface water, which this essentially can be interpreted as is that these waters, these brines, have been in a complete isolation with no input from the surface since the moment it sealed to the moment it was collected. In Kidd Creek, though, and this is data from the Canadian ship, it's slightly different. So I'm gonna essentially ignore the other mines that we're not talking about today. But for Kidd Creek, you also see a shift to the left. We're also suggesting here that there is low temperature exchange between the oxygen in the rocks and the oxygen in the water. And this is why we get the shift in composition. The difference here is that the Kidd Creek surface water, that is also around the global meteoric waterline, is actually, you see like the red squares, they show a little bit of a line that has been highlighted there. And this is because the surface water might have contaminated the brines that are sampled at Kidd Creek. This at the 2.9 level. The black squares at the 2.4 level are still quite, they plot quite without dispersion, and you don't see any kind of connection between the surface water and that. And then I'm going to go to the third question, which is what about the gases that are being dissolved from this saline water? So in most of these mines, this hypersaline water has been seen in tandem with these gases that are often hydrogen, methane, nitrogen, radiogenic noble gases, particularly here in argon. And hydrogen itself is mainly produced by radiolysis of water, and also water-rock interactions. You can also have, for example, circuit ionization, producing H2. There are certain things that we're going to be talking about later. The methane, on the other hand, may be of biotic or abiotic origin, which means is there life involved or not. The noble gases accumulation, as we've seen, normally will indicate long-term with isolation. And the hydrogen and the methane actually is important in this sense because, I mean, they're not indicating whether this is a long-term or short-term. You can't actually rely on them to give that information. But this is what is essential for sustaining deep microbial life. So this is where the interest in the extraterrestrial life actually comes through. So in sources of hydrogen, we have the cataclases of silicates in fault zones, for example, releasing hydrogen. You might have hydration reactions like circuit ionization, but one of the reactions that we've been seeing in the processes that actually is one of the most important in this kind of environments is radiolysis of water. So essentially you have the radiation hitting your water molecules, and through a series of very complex reactions, you actually will produce hydrogen. So essentially, like, is a fruit of ionizing radiation in the crust. If you have life, for example, and this is just to point out the extraterrestrial aspect, if you have life, for example, and you have hydrogen, then methanogenic bacteria, for example, can eat this hydrogen and then produce methane. So it's a source of life for them. And this happens in the crust whether you plan for it or not. It's just happening right now. So when we think about methane, which is one of the things that we are most interested in, also life aspect, in mine safety, from several points of view, we want to actually look at definitions. We have, for example, the left side here, the biotic is mostly what we think about methane when we hear the word. So essentially, for example, produced by methanogens. Or even, for example, like a cow fart. Everybody might have heard that they fart methane. Yeah, it's a biotic methane. You can also get thermogenic. For example, organic matter that has been buried, and then through all the processes, like end up forming all these complex C compounds. So, for example, oil here we're talking about. But what we're going to be focusing on throughout the rest of this talk is about the abiotic, so the right part of this slide. So we can have high temperature formation of methane, both in the mantle and through magmatic processes. So it's not that recent, but it has been shown by many studies, even recent ones, that methane can be produced in the mantle, especially like with reducing fluids. And now we are going to be talking about methane being produced at low and moderate temperatures through the entire crustal derives. So this is a compilation of all the, possibly not all, but the most important type of reaction that you can get to generate methane on Earth. So for example, through magmatic, you can have supposedly methane being delivered with extraterrestrial, so during formation of the planetary bodies, like you have high T reaction to the mantle. Late magmatic, you can have speciation of carbon, of oxygen, of hydrogen. And then with gas, water, rock types of interactions, the most notable one is actually number 9. So it's the Fischer-Tropsch type reactions. The sensu stricto FTT reaction is with carbon monoxide, but we also have Sabatier reactions that are with carbon dioxide, and this essentially get bundled into one single group, like so FTT, Fischer-Tropsch type. So when you see that there is a little technical difference, but I just wanted to mention that we are actually grouping more than one reaction into this. So one of the ways that we want to distinguish between origins of methane, so biotic, abiotic. So we see there's a large degree of overlap between the isotope signatures in all these graphs. This is the famous, like the pioneer work of Whittaker in 1999. So for example, if you have geothermal, hydrothermal crystalline might actually overlap with thermogenic associated in some cases. You have a site over there, for example, artificial bit metamorphic. I thought it was quite fun. But, or abiogenic. So just with this graph using carbon and hydrogen, you can't actually fully discriminate. So further research has been done. So when you actually show here, like this is from 2013, so there's still more data to be added. You can start seeing that there is a little bit of separation between abiotic and biotic gas, enough that you might have to get a sense like of what's what. But only with this, it doesn't fully help us, particularly if you're trying to separate thermogenic. So biotic and abiotic looks completely separate, or at least separate enough. But when you put thermogenic, it doesn't separate too well. So what do we do with this? Like we go down to our deep Earth observatory, or we go back to the field and collect more samples and try to figure out if there's a particular way that we can use field data, isotopes, and any other information that we can to be able to separate better this and constrain the origin. So the most investigated site, I think, to this point is Kidd Creek in Canada, which is in northern Ontario. And this is essentially automatically hosted massive sulfide deposit that is Archean in age. Currently it's a copper zinc mine, and there's historical saline fluids reported there. Also these reduced carbon rich gases that we've been talking about, and with a high noble gas content. And therefore we have the opportunity to have Toronto just very close by Timmins. You can take a drive. So there's 20 years of active research at this site, so you can actually not only sample once, but sample through time. So again, just to remind what we've been talking about, not just focusing at Kidd Creek, there's a water flow rate about 1.5 liter per minute. So this might sound little, but 1.5 liter of very saline water coming out per minute is a lot. You have this fluid can be a temperature, so it can be like up to 65 degrees Celsius. Yeah, because it has been at rock. And gas characteristics. So this gas exhaust is also at liter per minute ratios. Often, like it's more gas than water. Enriched reduced gases, carbon rich, and SS of noble gases, which has been used to constrain the up to 2.1 billion years of residence time. So what does the composition of gases look like? So Kidd Creek is the one to the right. So you can see that in our Canadian chute, you do have like methane and nitrogen and some alkanes. So essentially when you talk about alkanes and C2 and more, like it's ethane, propane, butane, you know. But Kid Creek in particular has hydrogen as well, has helium in very appreciable quantities, in addition to the nitrogen and methane. So several relationships have been proposed between the different hydrocarbons based on the carbon number and isotope compositions. So when we look here at thermogenic hydrocarbons, so C1 being methane and so on. For example, with thermogenic, when you measure your isotopes in the carbon-hydrogen space, methane will be probably lighter than the ethane, and that will be lighter than propane and so on. While if you measure Kid gases like C1, will actually change a lot more in hydrogen space, but not so much in carbon. So it's essentially the other way around. So in thermogenic, it's getting lighter and lighter and lighter and lighter in hydrogen, and heavier and heavier in carbon. In Kid Creek, the carbon doesn't change as much, but the hydrogen changes quite dramatically. On the bottom part, these are some of the data from South Africa. And you don't see as well organized relationships as you see at Kid Creek, but you definitely see that it's not the same behavior as thermogenic either. And on the right, on the other figure, when you see the carbon number and the composition of carbon, delta 13C, you see that the behavior between thermogenic and Kid Creek is also very different. We still can't affirm it's abiotic, but we definitely can say there's something here. So we're building up evidence that something's going on. We also use Scholes-Fourier distribution of alkanes essentially to be able to see. So essentially, Scholes-Fourier distribution is essentially the probability that, for example, methane has, or like a carbon species has, of adding one more carbon chain. So for example, for methane into going into ethane, ethane from going into propane. And when you calculate the relationships, like abiotic gas comes very close to a distribution of 1, so it's almost pure. And thermogenic actually will give you much smaller R squares. So that's another evidence that abiotic actually might be the source. And so for one thing that I'm also not sure if people have discussed a lot about are isotope logs. So now in addition to measuring isotopes, so for carbon and hydrogen, we can also measure molecules, let's put it that way. So for example, here we are looking at the methane that has 1 carbon-13, 3 hydrogens and 1 deuterium, versus the methane that has 1 carbon-12, 2 hydrogen, 2 hydrogens, and 2 deuteriums. And essentially what we see is that for one of the levels at Kid Creek, it has essentially a calibration line. It's going through a calibration line from higher temperature to lower. And in the red ones that are from deeper in Kid Creek, where we already had evidence for contamination, you see that there might be an impact of bacterial compositions in the methane. And now, just to conclude, I will talk briefly, I'm twice bigger, about the work I've done. So, as a Brazilian, I really felt it was important to me to go sample the deep subsurface of Brazil. We have plenty of craters there, and this had never been done. So we had lots of work here in South Africa, work in Finland, work in Canada, but South America was completely not known whatsoever. So I was able to visit 2 underground mines in Brazil that are in the southeastern part, and so I was able to sample this, and I'll show you what I got. So just so you know, so these are the mines, Córrego do Sítio and Cuiabá both gold mines, owned by Anglo Gold Ashanti. They were very nice to let me go down and serve their operations for 1 day or 2. So essentially, Córrego do Sítio is a much shallower mine. So the current depth of exploration at the time I went there to sample was around 350 meters. While Cuiabá was a much more established mine at the time, exploration depth was around 1.5 kilometers. And this was considered a dry mine, while Corrego do Sítio was a mine that was very, very, very wet. So we had plenty of evidence for water, meteoric water infiltration. So both of these mines are located in the San Francisco Craton, and actually at the border, in the southern border. This is very different from Kidd Creek in general, in the sense the ages are similar, but this has seen a lot of deformation across geological time. So you have this greenstone belt, and which we are sampling with the mines, also squashed with the middle supergroup, which is a Paleoproterozoic event that happened, and then you still had the collision of the Araçuaí Congo, and then the subsequent opening. So there's a lot of things that happened in this area over the last, let's say, 3 billion years, and it has been stable, not for long, too long, long enough. Anyway, so this is the area in Brazil where you might have heard because of the iron mineralizations. The iron mineralization of Paleoproterozoic, they are not in the Greenstone Belt. Greenstone Belt is essentially mined for gold. In both mines we had gases, so both of them had occurrences of gas. So in the case of Corrego do Sítio, we did have most methane. Methane was the most abundant gas. We had also nitrogen in appreciative quantities. And we had samples that went up to butane as well, as you see in Kidd Creek, but sometimes you only would see up to propane. The isotope composition here, you notice it might be a little bit lower, like so lighter, carbon-13C, delta carbon-13C. So I interpreted that to suggest that, at least for methane, there's a little bit of biotic contribution that might not be from the formation of the gas, but from subsequent interaction with the surface. But there's also supporting evidence for a biotic origin. I've not plot here, but the fluoride, so all the things look the same. The fluoride also looks on 0.99. So it is essentially the same as you would see in Kidd Creek. But for Cuiabá it was slightly more interesting. I have samples with 99% methane, for example. So I think everybody can appreciate how 99% methane can be a danger, like to mine operations. But in this mine it's way more heterogeneous, so depending on where you're sampling, you might get different gas compositions. And it also plots around the South African mines in composition of methane, slightly like maybe towards biotic gas over there for Corrego do Sítio, but still hard to know. And noble gas systematics, one thing I didn't mention about, because it's not about residence time, is that whenever you produce noble gases, like by, these reductive processes in Earth, they actually, like if the rock is Archean, if the basement is Archean, it produces noble gases at a different ratio than the actual normal crust. So you can see that our neon, for example, falls within the Archean crust, mixing line. But we can identify that there's no mantle contribution, there's Archean crust contribution for sure. Argon isotopes are also highly radiogenic, but I wanted to point out the difference here, because we cannot calculate the groundwater residence time just from this data. It has to have follow a specific procedure. So we have not been able to do that. And the water, disappointing, unfortunately for me as a geologist. I wanted to see those crazy saline fluids, not the maximum total of solids, 3.7 grams, very little. I've done some for isotopes in the water, so I can tell you that some of the sulfate in the water comes from the rock. High 2 have delta 33 of 2 per mil in these waters. But ultimately, everything seems to follow along the global meteoric waterline, which essentially means this somehow has been either not had time enough to, interact with the rock to shift the composition so much, or it has had some contamination. Oh, and just one thing here in this slide is that I also wanted to point out, you can have methane and all hydrogen and all these other gases without having the hypersaline fluids. apparently. Yeah. What does it mean? I still don't know, but I'll take suggestions. Challenge of sampling. Most of these things are word of mouth occurrences, so sometimes your mind knows it exists, but we don't know. And sometimes they don't talk to each other about it. If you are able to sample it, you are on Einstein. You cannot essentially like just go and do it. You have to follow the rules. You have to be available when they are available. If they're not available, you are not available. But again, if you get permission to go down there, you get better results in deep mines. And for example, in Brazil, actually, it was surprising to me. I found out there are actually not that many deep mines. It was most deep mines are actually not operative right now, so it's hard to sample anyway. And you have to be lucky that there's occurrence of gas or fluids in general when you're there, because sometimes it's, I was very lucky because both strips, the drill intercepted gas the day I showed up or the day before. Yeah. So if there's active drilling, you might have an issue. Like you can't tell them to shut it off just because he wants to get some gas. Some H occurrence might require different sampling methods. So you have to be able to be creative with what you have. And often confidential information is involved. So none of us can talk about what we want, or there's things we cannot talk about. And this is what it looked like in the last time I was at Cuiabá mine. So for example, the drill here at the left, because they had these gas occurrences, they had the sensors at the tip of the drill. When it intercepted methane, and the amount of methane rose, the drill shut in place to avoid accidents. And then we sealed the borehole and collected the gas through this device we had. So just wanted to thank everybody that helped us to do this, like both Corrigo C2 and Cuiabá, because the Ashanti folks were very, very generous with their time and their resources. The folks at the University of Toronto also that worked with me were very, very nice. And this research was funded by NSERC, which is the funding agency of Canada. And I'll take any questions. Yes?
Thank you for the interesting talk. How does this water compare the composition of these ubiquitous fluid inclusions which you have at different sort of rocks? For example, I know there are also people crush the rock, I don't know, in some isolated chamber, then measure the composition and isotope composition of gases. So are there similarities?
To be very fair, we tried to do but I am not familiar with the research of like other locations. Because I'd like to compare like the inclusions of the mine where it's located to the no, in terms of composition, not isotope composition, but the composition, Cuiabá mine has very similar fluid inclusions in, for example, quartz vein. You have methane and CO2 as well.
Yeah, great talk. You know, I don't know how do you say, how like realistic this is, but you know, there's been some talk about doing hydrogen exploration in the Kalkval craton from like subatonization and stuff. Like, is there? It seems like there is an isotopic way to identify hydrogen that's forming from the radiolysis versus subatonization, or no? Or, okay.
Not that we've done so far.
Okay.
I mean, I'm not going to say there isn't, but for example, when you look at these gases, if you have contribution from both,
Okay.
how can you tell? Like,
Okay.
It's all mixed already.
It's all mixed. Okay. Okay. Cool.
Nivea, you showed in those 5 samples from the one mine in Brazil quite a lot of variability in the methane contents and other gases as well, nitrogen. Is that predictable? Like, is on a length scale, like within the mine, can you inform safety using the distribution of the gases?
No. To be very fair, this is where it involves the confidential data, but these were collected in different levels, in different situations. And I think what I could say is that I think we did not expect the variability, but clearly there are multiple processes going on. We also have to think that if there's any chance fractures are connected, they can also have some funny things happening. But in this case, I would say if you are worried about mine safety, you have to be prepared to find the methane. And the relevance for this, just in case, like I should have mentioned maybe, is that at some percentages in the atmosphere, this is explosive. It's highly explosive. So when you're drilling, you might actually explode yourself. And this has happened. I mean, not particularly in this mine, but in other mines, including here in South Africa.
Can you comment on the Geotalk? Sorry. Can you comment on these isolated reservoirs and how? I mean, what would be the maximum residence time do you think they could live or be preserved for?
It's hard to know because our sampling is also biased. We can only sample if you happen to have a deep mine that goes below a certain depth.
Yeah.
So if we could drill deep enough to intersect this kind of fractures, we might have way more data, but we rely on places where you actually have exploration. So Kid Creek, as I've mentioned, I think is probably the longest or the oldest, the longest residence time that we've seen so far, around 2 billion years. So if 2 billion years is possible, like I don't know if you go drill a place where the rock age is 3 billion, can it give you 3 billion? I don't know.
And how big do we envision these to be? I mean,
Big,
some of them have been.
Crust. All the
Define
crust.
big. I mean, 100 meters, a kilometer.
Really, like in terms of fracture?
Yeah.
Wow.
I mean, if
I
they're
don't know.
isolated pockets of water, I mean, this is going to show up on seismic if they're big enough.
I
So-
know because this type of, the issue is that we only see these fractures more often, when they're intersected by drilling. So we're not actively seeing this with our own eyes or measuring how long they are. But some of these have produced for a very extended amount of time.
Yeah, I mean, if you
Years
have
with
the
water
volume
coming out.
of water that's come out of them, because water is incompressible essentially, you can work out the volume of the. I mean, is it a cavity? Is it? Do we know?
Fractures. The knowledge breakdown is fractures. So the ones I've seen in Brazil, so for example, the ones I've seen in Cuiabá mine, not the water but the gas, when they hit, I was able to see the core that they obtained from when it hit. And it looked like a massive carbonic recrystallization. So I think we're talking about more than just one geological possibility for gas formation, for example. For water, fracture, cavity, how we got trapped, I think fractures is the running model. In terms of so the estimates for how much water there is are made based on assuming a porosity of 1%, and that gives you, as I said, like I think between 8.5 and 13 million cubic kilometers in the crust. But here we're talking about all continental crust, because that's what I was mentioning. If you are we are sampling essentially where people are willing to pay to drill that deep. But if you went to drill, for example, in Amazonia, or if you went to drill in Australia, like that deep, you probably won't find the same thing. It's just that we don't have the access to do so.
I'm just wondering because we often where we're drilling to run into water, we also have seismic data. So I'm thinking, are we not?
I don't know. I mean, I'm not a
We haven't
seismologist.
looked in the seismic data for it.
Yeah, I'm not a seismologist, and it would be interesting to see if there's a way to predict where you can find this. But I don't know. I think at one of these mines they were doing also seismic. Okay, geophysics. I'm not gonna say seismics, but they were doing geophysics also. But again, confidential information. Hi, Karen.
I was just thinking in terms of fluids that are responsible for diamond formation and how fluids in the crust may vary with fluids that we see in the mantle. And so for diamond formation, they often model carbon-bearing fluids as either oxidized as either carbonate or CO2 bearing. And so I was just curious whether any of these fluids in the deep crust have been shown to be oxidized, or are they all methane hydrogen bearing? Are they all reduced fluids?
I'm not sure I've seen CO2 before. I mean, I might be confusing with because he asked me about the fluid inclusion.
Yeah.
I've seen fluid inclusion of CO2 for sure. Like, so I.
But the gas that you're actually collecting is mostly methane and hydrogen.
It's also made of methane.
Yeah.
Hydrogen, sometimes there, sometimes no. Hydrogen, methane, and also other higher alkanes.
Okay, but not oxidized, always reduced.
I'll have to take a look, but I can't remember immediately. Because again, like there's more, I mean, I'm more familiar with Brazil, of course, because I collected, but also with Moab, with Hitpree. I can't remember any of these, but I don't know about the other mine in Africa, like maybe. I'll take a look at it.
Yeah.
Okay. Thank you, Nivea.